My name is Timur. Thank you very much for waiting and bearing with us as we set everything up. I want to talk today about contracts for C++. Before I do that, I want to talk about something else. So I used to live in London until a year ago, and then I moved to Helsinki, Finland. And I was very surprised that there was no meetup going on. There's plenty of C++ in that area. So I started one. And it is now the northernmost C++ meetup in the world. The first one was basically just me and 15 other people who just showed up when I said, hey, anybody wants to talk about C++? And we met at the pub. And, there were like 15 other people there. It was kind of fun. But then somebody actually gave us a room and somebody came with a talk. Then it kind of grew and grew. And this was May last year, right? And so now we had our last meetup in January, and we stabilized somewhere between 90 and 100 attendees we have every month. So if you ever want to travel to Finland, it's beautiful. You should do that. You should visit me and visit our meetup. And if you want to speak at our meetup, you can do that too. It's always worth a trip. It's a beautiful country, nice place. Come to the C++ Helsinki meetup to give a talk. I'll show you around. You can do the sauna. You can try the reindeer and like stew and all that. It'll be great. And then you can do talk.
The whole touristy thing, basically, right?
Right.
The tourist package.
If you want to visit Helsinki, it's a great place, and we have a C++ meetup. And lots of C++ jobs in the area as well. So you can find more info about that at meetup.com/cpp. Right, now back to our actual topic. I'll talk about contracts for C++. And we're going to talk about what contracts are, what they're for, what a contracts facility is, which is kind of the thing that you want to talk about, like the language feature. And then you want to talk about P2100, which is the current proposal for adding contracts to C++, hopefully in C++ 26. A bunch of people, including myself and Gaspar, who's here in the room, and many other people have worked on for quite a few years now, and which is now finally design complete. And it's kind of making its way through the committee, and hopefully will land in C++ 26. So I want to talk about all of that. How much time do I actually have now that we started?
Well, I think we started. We lost 10 minutes.
Okay.
Lost 10 minutes. You're now in 20.
All right. So by 9. Okay, let's see. Let's see how far we get. So what are contracts and what are they for? Well, the term was coined by Bertrand Meyer, I think, in the 90s. And so design by contract is this kind of approach for software design, which in its original formulation prescribes that we should define formal, precise and verifiable interface specifications for software components, which extend the ordinary definition of accelerator types with preconditions, postconditions, and invariants, which we refer to as contracts, in accordance with this metaphor with conditions and obligations of business contracts. And so we have here preconditions, postconditions, and invariants, which are kinds of contracts. That's kind of basic terminology here. So a contract is a set of conditions that expresses expectations on what a correct program is. And we have 3 kinds of them. We have a precondition, which expresses the expectation on a function when you call it. And then we have a postcondition, which is an expectation on what happens when the function returns. And then we have invariants, which are expectations on things that stay the same throughout the lifetime of an object or throughout the execution of a loop or something like that, where every time the loop goes around, every time you do something with that object, those things don't change. So those are kind of the main types of contracts or kinds of contracts. And here's some other terminology that we'll need. A function that has no contract, function that has no preconditions, we say it has a wide contract. And a function that has preconditions, we call having a narrow contract. And so if we have a function with a narrow contract, so it has preconditions, and we call it and we satisfy the preconditions, we say that that's an in-contract call. And if you don't satisfy the preconditions, then that's an out-of-contract call. And whenever you violate a contract or part of a contract, such as a precondition or a postcondition or an invariant or whatever, it's called a contract violation. So this is kind of terminology that's going to appear throughout the talk. So I just want to very clearly like define those things. I should also say that because of the weird setup here, I'm not seeing what the next slide is, and I only finished making the slides on the bus on the way here. So I might stop a few more times than usual and be like, okay, what's the next slide? I don't remember. So please bear with me. It's now all a bit improvised because of the unusual setup. So it's very important to recognize that a contract violation is not an error in the sense that being out of memory is an error or reading corrupt data is an error. A contract violation is a bug in the program. It means your program is incorrect, you wrote the wrong code. And so typically the only way to mitigate that is to fix the bug in the code, by changing the code, right? So what happens when you violate a contract, such as a precondition? What happens when you call a function out of contract? Well, a lot of different things can happen. But in general, it's undefined behavior. Particularly in the C++ standard itself, we have the specification of all the functions in the standard library, which have all of these things. Constraints, mandates, preconditions, effects, blah, blah, blah. And if you look here, it defines preconditions and postconditions, which are kind of the contracts of every function in the C++ standard library. And it says that a precondition is a condition that the function assumes to hold whenever it's called, and violation is undefined behavior. Right, so the compiler can just assume that if you have a precondition that vector operate a square bracket, get the index, and it's not out of bounds, it can just assume that, and if it is out of bounds, then nobody knows what you're gonna get. Crash code that does something undefined behavior. So,
and if you call a lower bound with an unordered array, you're also gonna get garbage, right?
So let's practice this a little bit to make sure we understand what a wide contract is and what a narrow contract is. So we all know std vector, right? So std vector size, does that function have a wide contract or a narrow contract? Does it ever undefined behavior to call this function? No. So that has a wide contract. Okay, what about vector empty? Wide. Okay. Operate a square bracket, narrow or wide? Narrow. Okay, so undefined behavior to call it with an index that's out of bounds. That has a narrow contract. What about vector at? Wide. Okay, so that's the difference, right? It's an error to call vector at with an out of bounds index, but it's not a contract violation, right? Because it's always valid to call it. It's either going to throw or it's going to give you an element, right? But this is all within the domain of the. So that has a wide contract. What about vector front? Narrow. Okay, so that's a very important thing. It's not just about the parameters, the arguments that you pass into the function, right? It could also be about some other state or that the object or something else in your program is in. So vector front doesn't take any arguments, but it has a precondition that the vector is not empty. Right? If it's empty, you call front, you get UB. So narrow contract. Vector back, narrow, wide. Narrow. Okay, same thing. Vector reserve. Wide. Okay, you're good at this. Vector begin. Wide. Vector end. Vector swap. Okay. So it depends. Right. So there's this weird thing if the allocator points, if basically the allocator is swappable, then it's fine, and otherwise it's undefined behavior if it's not the same allocator object inside the container, right? So it depends on the type, what kind of allocator you have in the vector. Okay, so that's what contracts are. What are they for? Like, why do we define these preconditions and postconditions? And what's a contract facility? Okay, so how do we specify contracts? We can specify contracts in a number of ways, right? We can specify them in documentation. I think is that question there?
Yeah. Sorry. If a class has an invariant,
Yes.
does me calling a member of that class wide or narrow? A class has an invariant. If I mess that invariant up somehow through reinterpret cast or whatever, is calling that member of a class is wide or narrow?
I think it depends on the implementation, but certainly there are cases where the implementation would assume that the invariants are holding.
It's narrow. You can, and the way you know that is the object of that you're calling the member function on is just another input to that function. And so if that object is in an invalid state, you're calling that member function out of contract. because it assumes a valid object, right?
Mhm.
But crucially, the contract facility doesn't care what you think is a wide or narrow contract. What it cares about is something else. But yeah, for the purposes of nomenclature, that would be a narrow contract if an invariant is not satisfied.
All right. Thank you, Kashmir. So how do we specify a contract, whether it's a precondition or a postcondition or an invariant or whatever? So the most common way to do this is to just do it in the documentation, right? So have a comment above the declaration saying it's undefined behavior to call it this function with the wrong arguments or something. So that is a contract, right? Another way you can do this is in some separate document, like in the standard itself, right? The C++ standard defines its contracts just in the standard, also with English specification. So that's one. Or we could specify the contract in code, right? We could have some syntax, which we currently don't have in C++. Well, it's a precondition that pause is smaller than size, right? We could specify these things. And so when we do that, oh, and I should say, if you don't do it in code, we call that a plain language contract, right? We do it in code, we call it, for the purposes of this talk, contract assertion. That's like a really, really important distinction. When I just say contract or precondition or postcondition, I mean the conceptual thing. Whether it's defined as a plain language contract or as a contract assertion, right? So I don't necessarily mean the thing that's specified in code when I just say contract. When I say contract assertion, then I mean the thing that's. So if we have some way to express a contract assertion, like the proposal we're going to talk about for the rest of the evening, then you can define something like this, pre, and then you have a predicate here, which is essentially an algorithm to check if a contract holds, right? And so in the simplest way, this is just an Boolean expression, right, that evaluates the rule like this. If it's true, you're good. If it's false, you have a contract violation, right? And so a language feature or maybe a library feature that allows you to do this, right, that lets you define contracts in code with contract assertions. That's what we call a contracts facility. Okay? That's the terminology. And if you have this facility, then checking certain contracts, sometimes you can do it, sometimes you can't. Right? That's also really important. So sometimes it's very straightforward, like this precondition of operator square bracket. You can just easily find an expression, put that into the code if you can do so, but the language lets you do that. Then you can check that aspect of the contract, this particular precondition, programmatically. Sometimes you can express it in code, but it's very expensive to do this check, or it actually violates the algorithmic complexity of the function to do the check, right?
Which is part of the contract.
Yes, exactly. Part of the contract of binary search is that the complexity is log n, but checking its precondition is on, right? You might not want to do that, unless you have some kind of special super debug mode that gives up these guarantees. And sometimes it's impractical or even impossible to check programmatically if you don't have special instrumentation, right? For example, anything that has to do with memory safety, like is this a valid range? Does this pointer point to a valid object? Those are very common preconditions. You cannot check unless you're running some kind of sanitizer or other kind of instrumentation that tracks the memory. You can't just do it as a C++ expression. And finally, there are preconditions and postconditions that you can't check programmatically at all. Like you pass in a function to another function, and the precondition is that that function halts, right? In general, you can't prove that. Maybe in some cases, but in general, that's the halting problem that's citable. So that is a precondition that you cannot check in general programmatically at all. So the really important bit here is that contract assertions that you specify in code, they always just can express a subset of the actual contract, right? Not necessarily the entire contract. So it is perfectly normal to have part of the contract of a function expressed as a plain language contract and not with contract assertions, right? So if we have contract assertion, that's typically just a subset of the actual contract. So why do we need this kind of facility that lets us do these contract checks programmatically? Well, there's a lot of things. Obviously, for self-documenting code, right? If we have it's always better to express things in code rather than in comments. And rot, right? You can get out of date. We can check these things at runtime, right? Like an assertion macro. We can check them at compile time. We can feed them into a static analyzer that's going to say, oh, well, I can kind of reason at compile time that if you do this, you're going to violate this precondition. You can do formal verification with it, which is like the next kind of step of that. Or you can feed that into an optimizer and say, hey, just assume that all my preconditions and postconditions are true and optimize based on that assumption and make my code go faster. So those are all things you can do as soon as you can express contracts in code. And it turns out that C++ actually already has a contracts facility. What is it? Assert. Of course, we all know C assert and we love it, right? So we can do this today. But it of course has a lot of problems. For runtime checks, you can't put it on declarations because it's a function like macro. You can only put it in the definition in the function body. You can't really customize the behavior, right? You only exactly have two options. Either you token ignore the whole thing, or it calls terminate when it's false, right? And you can't really access any information about what happened. Like it's going to print it to the console, but you can't programmatically access that information, what actually went wrong and where. And of course, it's a macro, so it has all these problems that macros have. Like you can't put like curly bracket A, comma B, curly brackets in there because the parser is going to break. And there's
You also can't put it into inline functions and headers because ODR violations.
Yes, so there's lots of problems with macros. You get all of them with this. So that's not great. You want something better. And you want something better as a language feature and not just as a library feature, because that's what everybody's doing, I'm sure, in this room. Or hands up if your code base has a custom assert macro because C assert is not good enough. Okay, so that's like almost everybody. So we could do this as a library feature, right? We can just have a better assert macro, and everybody's already doing that. But we really need this as a core language feature. And here's why. You want to be able to put precondition and postcondition assertions, and note that I'm saying precondition and postcondition assertions and not just precondition and postconditions, because that's the conceptual thing. Very important terminology distinction. So we want to put these assertions on declarations, so they're in the interface. So you're in the header, you see them, right? You want to use them portably across different libraries and code bases. You can't really do that if every library has their own custom assert macro. You want to be able to fully customize that behavior. You want to be able to access information about what went wrong, for which you kind of, if you want to do it well, you need compiler support for that. And one really important thing is you want this to be accessible for tooling, right? So if you have some kind of static analysis tool or an IDE that can color things in a fancy way and draw some pop-ups if you violate something or whatever these tools do, like you want to have a standard syntax that all these tools can consume, right? So for all of these reasons, we need a contract checking facility as a core language feature, and we don't have that at the moment. So let's see. Yeah, there's a question.
Could we say that assume is also a contract facility?
Yes, but it only has one contract semantic, which is the assume semantic, which is the one that you cannot actually use for anything that has to do with correctness or finding bugs. But it's the one that you can use for optimization, yes. But again, you can't put it on a declaration, only in a definition, and it's an attribute, and it has its own problems. But yes, I would say assume is kind of, in a weird way, also a contracts facility.
What about unreachable?
What about unreachable? Well, unreachable really is just assume false, isn't it? It's just a different way. So, yes.
So the answer is yes, no, maybe, no.
So let's have a contract facility in the language, C++, right? That would be great. Why do we not have that yet? Well, it's a tragedy in 4 acts. Or I think another analogy would be, I don't know if anybody's into like the Marvel, like MCU, like they have these phases, phase 1, 2, 3, and then phase 4. And it's kind of similar like this. There's like 4 phases. The first phase was this first proposal, which was 20 years ago now, was the first proposal to add a contract facility by Thorsten Ottosen, which was inspired by D, the D language, and kind of work the same way as it does in D. You have these precondition block and a postcondition block, and you can put a bunch of statements in there. So you can also have multiple lines in those curlies. You can put all kind of stuff in there. And it was kind of working in the way it does in D. And so that went through quite a few revisions. It attracted more authors that helped out with it. It kind of grew and evolved for a few years. And then in 2006, the paper trail ends. I don't really know what happened to it because that was way before I was on the committee. But apparently the committee at some point said, no, we don't like this direction. I would actually be curious if anybody knows what happened to this approach, but like the paper trail kind of ends, and then there's a bunch of more papers that are looking at contracts in general and how we could do it. But like this particular direction, like wasn't pursued further. Then the next serious attempt at adding C++ contracts to the standard started in 2013 by John Lakers and a bunch of other people from Bloomberg, who had a contract facility in their code base for already 20 years, which is the BDE. Yeah. So they have a bunch of cert macros there, which are very customizable and do lots of stuff. And so they tried to standardize something very similar to that for C++. And it also went through a few iterations with like first there were macros, then there were like function-like things, and first they were all in capitals. And the latest version of this had this syntax, which ironically is exactly the syntax we have today, except we also have more stuff. So back then, could write these contract assertions, but that's the only thing you had. And they could also, again, only go in the body. They couldn't go in a declaration. So quite limited, similar to the assert macro. Can do a lot more stuff than the assert macro, but still not quite as much as you want. So the committee said, no, we don't want that. So phase three.
So that was library only, the main cost.
That was library only, yeah. That was a library solution, which has these drawbacks, like can't put it on a declaration, you don't have like language support and stuff like that. I mean, it was already a lot better than the assert macro, but like not quite what the committee wanted at the time. Phase three then started about the same, like basically started because this Bloomberg thing kind of failed, and then the Bloomberg guys and a bunch of other people who were thinking about this problem, like Daniel Garcia and Gabriel Reyes and Bjarne Strostrup, they kind of all got together and, okay, how can we put together all of these different ideas and come up with something better? And that kind of resulted in what we had at some point in a C++20 working draft. That was something like this, where you have preconditions and postconditions and also assertions, and they're spelled with these double square brackets. So they're almost like attributes, except not quite, because there's this colon here. And so this has evolved over 5 years and got better and better. And at some point it was in the C++ working draft. People found a bunch of problems with them. They got removed again. There was lots of drama on the committee that I'm not going into right now. Ask me later at the bar about that part. But so they got ripped out in it from C++20, and we didn't get that. So that was the kind of moment where we were like, oh, okay, so we need to start over. So there was a lot of tension there. People really didn't agree, like at the end, what contracts were even for and what they were supposed to do. So we kind of had to start from scratch. We have in the committee this like three-stage pipeline, and the bottom of the pipeline are the study groups. So we created a new study group, SG21, for contracts. And so this group has been busy now since 2019. So it was almost 5 years that we've worked on this problem, and resulted in this paper, P2100, which a bunch of us are authors on. It's a collective work of a lot of people over the last 5 years.
The integration of probably like at least 10,000 emails and maybe something like at least 25 papers.
Yes, it's a lot of human hours that have been sunk, probably human years, but tens of human years that has been sunk into this. And we call this the contracts MVP. That's our current proposal. And so we at some point realized that we really want to get this into C++26, but time is running out, right? So we basically worked back from that and said, okay, if you wanted to have in C++26, then we have to have the wording completed in 25. We have to have the design review completed by this date. So kind of we worked back from it and came up with this timeline, like by which things need to happen. So we have 3 committee meetings a year. Right now we have the next committee meeting starts just in 2 weeks in Tokyo. And we said that if you want to get this into C++26, you kind of really have to be design complete like by this Tokyo meeting. And then we can port it to the design review group. And then when they're happy with it, we can forward it to the wording review groups. We have this three stages. But however, we then at some point switched to weekly telecons and like really intensified, like because there were so many design questions still open that we're like, okay, we need to like ramp it up. And if you want to figure this out in time. And we did such a good job that we actually already design complete as of last Thursday. This is then. Hear this. That we are now actually ahead of schedule. We a couple of weeks before the Tokyo meeting managed to finish this paper and we're now design complete. So now we voted to pass it on to the design review group. That's like the next level. And they're going to look at it in Tokyo. And it means it still might change. I already heard that this other group said, oh, I don't like this part. I don't like this part. So things still might slightly change. Yeah. So don't trust that what I'm going to present here is going to be like in the C++ 26 in exactly this form. Things might change, but since the study group has worked on it for 5 years and we are happy with it, I think it's hopefully not going to change substantially. So this is kind of a snapshot in time. This is where we are. We forwarded this to the next group. This is the design at the moment.
Well, we already have 2 in-flight diffs to it. So.
Right. So things are very fast, but this is a good milestone to give like a kind of a bit of a report on where we are right now. So the problem with this is that, as I said, you want a contracts facility to be able to do all of these things. So you want to really have, and so this is just a very oversimplification. Right? So the first thing, or one of the first things that happened in SG21 after it got ripped out of C++20 was that we sat down and actually compiled all the different use cases, all the different things which people might want to use contracts for, because it turns out the reason why it took 20 years to get here is because it's really so complicated because there are so many use cases for it, right? That roughly fall into these 5 buckets. But there are also many sub-buckets in those buckets, and different people want to use it in different ways for different things. So it's very difficult to agree on like one design that accommodates everybody. So we compiled like use cases for contracts. That was back in 2020, and that paper contains 196 use cases. So, right, ways in which you want to use contracts. So that's quite a lot. So kind of what people want is this thing. It's an animal from German folklore. It's the egg-laying wool milk pig. It's the thing that does everything, right? It lays eggs, gives milk, gives wool, and it also gives you tasty meat. And so it does everything all at once. And that's kind of what people want out of this feature. The problem is that if you were to design this, it would take another 20 years, and probably we would discover more problems than we actually agree on new features, and we would never agree on anything. So that isn't really the way to go. You want to reduce it and propose a minimal feature set and then build up on that and add more stuff later, right? So what's kind of the core, the minimal core on which we can all agree is useful? And it turns out that then we had another problem. So this is a fable from Russian folklore about the swan, the pike, and the crab, which are trying to pull a cart out of the mud, but the pike is pulling into the water and the crab is pulling sidewards and the swan is pulling up, right? And so they're pulling in different directions and the cart is not going anywhere. It's a very famous fable that anybody who grew up in Russia knows about this. So we were kind of stuck in this situation then for a little bit, like different people were just pulling in different directions. But we finally managed to like kind of make progress and decide, okay, this is kind of roughly the shape in which you want it to be for the first release, and then these and these and these things we can add later. And once we had this rough understanding, which was changed a little bit, but once we had this rough understanding, we then started making quite good progress. And so we decided that we can't really fully give everybody like everything out of all 5 buckets in the very first release that's going to be in C++ 26. So we got this one, right? So if you can express preconditions, postconditions, and assertions in code. So we got this one. We also got this one, runtime contract checks. And that's kind of really the meat of the proposal. That's what you're heavily focusing on, right? So what you want is you want to have a better replacement for CAssert and a better replacement for custom assert macros. Nobody should have to write assert macros anytime ever again. Because this facility is just going to give you a much better way to achieve the same things, right? So you got customizable behavior. It can go in declarations, which macros cannot. And like reason about what happened and
doesn't cause ODR violations.
And no ODR violations. And like we'll solve a lot of problems that you have with custom assertion. So it's going to be really, really, really much better. So this is kind of really the focus of this initial release. Focus on runtime checking, replace assertion macros. So these 2 cases, like we don't not support them. Like we have a syntax And if you have a tool like a static analysis tool or whatever, which can parse the syntax and do something useful with it, great. We don't prevent that from happening, and I'm hopeful that tools will use those things. But we don't have any special features targeted at aiding that specifically. We don't have anything to say, for example, a contract predicate must be checkable statically and must be const expr or must not have side effects. So you might have predicates that are not checkable statically, right? And we don't do anything special to like prevent that, right? So you don't really focus on those use cases. But you can still presumably have a static analysis tool that does something useful with these things. And we can build on that in the next version. We can maybe add features that are targeted more towards those. And finally, this one, like we don't do at all. The reason for that is that optimizing based on the assumption that a contract predicate is true has caused quite a lot of controversy in CSS20. That was one of the reasons why it got removed, because people were like, oh no, it adds undefined behavior everywhere. And like, this is bad. And no, it's not if like you fit it into this facility properly. But in the current political climate where everything's about safety and security, and anything that might add new UB is kind of, okay, we want to do this as a separate paper. Like we don't want to do this in the first release. You want to have a separate paper explaining how this fits in and do that separately so it doesn't endanger. If it creates more discussion, it shouldn't endanger the core feature set. So you're going to do this separately as an extension. Gaspar has a comment and then there's a question back there.
I mean, what you said is roughly true, but given the amount of implementation defined wording in the paper, the implementation is completely free to implement an assumed semantic.
Yes.
But so it's not like, it's more like a
Okay.
than an
Fair
X.
enough. I'll fix that in the next version of this slide deck. And there's a question back there.
Yeah, they compile out, right? If you want to.
No, they don't compile out.
Oh,
We get to that. We get to what they do. They do not token out like a macro.
No, they not token out, but they do. You have the option to not generate any assembly from them.
Thank you.
We'll get to that. So we have a few design principles that help us make certain design decisions. The first one is that if you have a context specifier on a function declaration like pre and post, it should always specify a subset of the plain language contract of that function. So that has two components to it, right? It should be always a subset of the contract, as we saw. Well, you cannot necessarily always express the entire contract, but you can express a subset. And the other aspect of this is that it should be the contract of that function and not the contract of some other function somewhere else. So we don't do anything like magically inheriting contracts from other functions that you didn't write on that function. Like we don't do that stuff. Like it should be right there, like on that function. And the second one, but that's a main difference to CSS20, which fixes a lot of problems, is that if you add a contract version to a program, do not change the compile time semantics of that program. It should never be in a situation where you add an assertion to your code and then it changes the program, and then you end up in a different branch where the bug you are trying to find doesn't exist. So you have this kind of Heisenberg, right? You add an assertion to find a bug, but then you end somewhere else where the bug doesn't exist. That's bad. You don't want that. So contract annotations should not be seen by concepts. They should not affect override resolution or type traits or whether something is no except true or no except false, which drops you into another branch of an algorithm potentially. You should not be able to sphere on it, right? So they should be completely invisible to any compile time reflection thing, right? That's kind of one really important design rule. And the other one is, which is kind of similar, is if you add a contract annotation but you ignore it, it should not actually do anything, right? It should never trigger something being copied or something being destroyed or something else happening at runtime if the semantic is ignored. So we can check something or ignore it, right? And if you ignore it, that should not have any runtime overhead. As Gaspar said, it should not create any assembly. So we want to have that in there as well. Finally, preconditions and postconditions, that's a very common misconception. People are like, are they part of the interface or are they part of the implementation? Turns out they're kind of both. They sit right in between, right? They're kind of part of the interface because they're on the declaration, but they're also part of the implementation because they can look inside and look at private members and things like that. So they're kind of like, if there's like a cell, like a biological cell, it has like a membrane and you have these like channels that are like going through the membrane and let things in and out. So it's kind of like that. It's kind of It has an inside part and it also has an outside part. So if you think about it as part of the interface or as part of the implementation, you think about it wrong. It's kind of the thing that connects both of them. And there are going to be parts of the actual like mechanics, how it works, where this becomes important. One more thing that is a massive difference to C++20 is the facility does not add any new undefined behavior to the language. C++20 contracts have stuff like, if your predicate has side effects, that's undefined behavior. And if you do this and if you do that, that's undefined behavior, because they didn't know how to specify some things. So they just said it's UB. We don't do that. If you don't know how to specify something, you make it ill-formed, or you figure out how to specify it. We don't add new UB into the language. Contracts are not unit testing. That's also very important, right? They're kind of a different way of verifying your program. And that's another one that we already talked about, is contracts are not error handling. Like, you shouldn't use contracts to check, to basically do code control flow for handling certain cases programmatically. You should use them to find bugs in your code. But if you're not interested in that, you can switch them off. So they're not a reliable control flow mechanism. You can't use them to catch user errors or system errors or anything like that. Only for identifying bugs in your code. Okay, so I still have some time. So we can talk about the actual proposal, the syntax. Well, we had, there was a syntax war going on. It took several years, but we finally sorted it out at the last meeting in Kona in November. This is our new syntax. Preconditions go in the declaration and they're spelled with pre, paren, predicate, paren. Okay. That's a precondition assertion. Post-condition assertion is spelled post, paren, predicate, paren. And there's one special thing in there. You can optionally refer to the result value. So the value, the object that the function returns. You can refer to it by introducing an identifier and then colon, and that's going to be the return value of that function. Here you can assert that the return int from f is going to be not 2. Or why you want to do that is like a toy example. But it's a post-condition assertion, and R names the return value. Up here,
And if you want a glimpse of why this was so difficult, think of what decal type of R is. Okay, but
it was
that's where I want to
figure
stop.
that out. But like, read the paper. Like, there's lots of papers that explain how all of it. Right. So the return value name is optional. Pre and post are contextual keywords, so they're going to only be parsed as pre and post if they're exactly in the syntactic location, which is at the very end of the declaration, or the semicolon. You can still use pre and post everywhere else for function names and variable names and whatever. It's fine. Not going to break any code. The predicate is an expression contextually convertible to bool. And grammatically, if you look at the C++ grammar, I don't think many people do regularly, but like in case you do, it's like a grammatic production which is called a conditional expression, which excludes assignment expressions. So you can't have. It's the same for assume actually. It's the same thing. So it's a way of specifying in the grammar that you can't write x equals 0. Syntax error. That's going to guard you against the typo if you want to actually write x equals 0. So you can write x equals 0, but x equals 0 you can't write. You have to put extra parens around it. Otherwise, it's a syntax error. So it's just like a little thing to like prevent this particular type of pattern. And then we have a third kind of assertion, which is contract assert, which is just like an assert used to be in the middle of the body. It's a statement. Contract assert is a full keyword, and we really would have liked to just use the keyword assert, because that's what every other programming language on the planet does with it. Unfortunately, we can't do that because assert is already a macro. And we spend a lot of time trying to retrofit it somehow that we can reuse the keyword, because the default behavior is the same. Default behavior is you check the contract predicate, and if it's false, you print some information and terminate by calling abort. That's exactly what contracts do. So the default behavior of contract assert and default behavior of macro assert is exactly the same. So we were like, okay, can we like, but it doesn't work because macro assert, if you define ndebug, macros out the whole thing, and that's not something you can do with contracts. And it wouldn't make sense. It would violate the principle that you don't want it to be compile time detectable. And if you token something out, you don't ODR use it, that might trigger some stuff somewhere. You can sphere on whether something is ODR used. So we can't do that. So there's no way to make it backwards compatible with assert. So you would either end up in a situation where you break macro assert, or assert means different things in different contexts, and neither of them are, like both of them are a non-starter. So we had to choose a different keyword, which we spent a lot of time also doing, and considered like 100 different keywords. This is the one we landed on. I think that's good enough. So context assert it is.
And there's another reason why this was so difficult. The C committee also expressed interest in using the same syntax that we choose if it's going to be compatible. So that was another. Like, it goes past the committee.
So basically every slide in this talk, I could probably talk for an hour about like how we came to this decision, but I'll spare you that. Anyway, so here's how this works. If you call F with 0, you're good. If you call F with 1, you violate the precondition, you get a contract violation. Call F with 2, violate the post condition because the return value is going to be 2. 3 violates the assertion statement inside, and 4, you're good. So every expression is just converted to bool and evaluated. Okay, so where can you put these things? Pre and post you can put on the function declaration. You have to put it on the first declaration. You can optionally put it on a redeclaration. If you have an auto return type, that declaration has to be a definition because otherwise you don't know what the return type is and you can't write a post condition. You can put it on lambdas. Product assert is a statement, so you can put it anywhere you can put a statement. That's in general anywhere in a function body. It was an expression at some point, like macro assert can be used as an expression. This is just a statement. There are interesting reasons why it can't be an expression. Talk about it at the bar if you're interested. It has to do with no except. It's not straightforward.
There were multiple papers.
You can't have pre and post on deleted functions because that wouldn't make sense. You never evaluate anyway. You can't have them on functions that are defaulted on the first declaration because equals default means you just get the default interface, which pre and post are not part of. And it will also break, it would break trivial functions in interesting ways. So like, can't do that. Can't put them on function pointers. That would be also really weird. What? Yet. But then if you would do that, they would kind of be part of the type and we kind of don't want that and it's complicated. So that's not really, not yet. No pre and post on function pointers, no pre and post on coroutines. You kind of contract assert on a coroutine, but not pre and post because what would that do? That's another very long paper about this. And you can't have them on virtual function. That's the only one that's kind of, we really kind of want that, but it's another really non-trivial problem. So we decided, we are pretty confident we know how to solve it, and we're pretty confident we're going to solve it for C++ 26, but we're going to do that as a separate paper because it's just a rather complicated piece of work to like figure out how to do this correctly. Spoiler alert, Eiffel, D, and Ada, none of them got that part right. Like complex and virtual functions are basically broken in all of these languages. So we want to get it right, but we don't want to delay what we already have for that. So we want to do it as a separate paper. So in this MVP paper, no virtual function support, which I know, excludes a lot of C++ code, but hopefully we'll still get this in C++ 26 as well, just not in this paper. Name lookup access control for pre and post works as if it was the first statement in the function body. So for example, here you can actually access the private variable in pre, though it's on the interface. One of those examples where it's kind of the interface, but also the implementation. You kind of want to have access to private variables there. The name lookup works as if it was in the body. That's another one that was very interesting. So local variables are implicitly const if you refer to them in pre, post, or contract assert. So here the red ones, you are trying to modify either a parameter or a local variable. And that's an error. They're implicitly const in the same way that they're implicitly const in a const member function. Okay. In a const member function, everything's implicitly const. Same thing here. So that holds for variables and for references, not for pointers. So it's a shallow const. If you have a pointer, you can still dereference it and modify the object behind the pointer. You can modify global variables. You can modify static variables, just not local ones.
Don't do it, but
and you can, if you really want to, you can circumvent that by static casting it to non-const. But then You're kind of on your own. If the object then is actually const where it was declared, then you're in UB land, right? So don't do that. So this is like a pre and post and context assert are things where you check the state of your program. You shouldn't be modifying the state of your program. That's bad. So we're trying to prevent you from doing that. But if you really want to, you can still get the crowbar and do it anyway because here's another one. So if you're referring to a parameter in post, that parameter has to be declared const. And that makes a lot of sense because if you did not have that rule, let's think about this function clamp, right? So it takes a min and a max and a value and it clamps the value to within the min max. Right? So the post conditions of that are pretty obvious, right? These are the post conditions. But if we didn't have this rule with the const, we could modify the parameters and then still refer to them in a post condition. Right? You wouldn't really be able to reason about what value you're referring to. Are you referring to the value that's parameter where it's been passed in, or some other value because it's been modified in the body, which you don't see if you're on the declaration. You don't even see the bodies. You have no idea what values you're actually referring to. And it turns out this implementation, if it wasn't const, would actually pass the post condition, right? You just set everything to 0 and return 0. Post conditions hold, right? That doesn't make any sense. We don't want to allow that. So if you refer to parameter in a post condition predicate, it has to be declared const. All right, what else? You can refer to the result value in post, as we already said. Right? You can write r colon or ret val colon if you want, and then you get access to the result object. And this is actually really fun because you get access to the actual object that the return value has been assigned to. Because if we initialize an object here with the result of that function call, by the time the post condition has been evaluated, that object has already been initialized, right?
Because copy elision.
Yes, so that's really cool. So you can pass in the address of this object here, and then you can check the address in the post condition, and you get the address of that thing, right? Except if it's trivially copyable, because then it could be in a register and it would be an ABI break to allow this. So we don't require this for trivially copyable types. Yeah, but don't worry about it. Again, modifying the result value in post is an error. They're implicitly const. Because it would be really weird if you check whether the return value is correct, and then you actually modify it as you do that. That's really bad. Like, that doesn't make any sense. So they're implicitly const. Again, you can const cast your way around it if you want, but just don't do that. This is a fun one. So you cannot trigger an implicit capture from a context expression. Right? So if you have a lambda here, and you refer to something here in the lambda that would be default captured if you add this thing, but otherwise isn't mentioned anywhere. So it would only be default captured if you add this context assertion. And adding the context assertion would change the size of the closure type, would change whether it's implicitly copyable and things, trivially copyable and things like that. It could potentially trigger an additional copy that wouldn't happen otherwise because it's just ODR use, right? ODR using something triggers a lambda capture that's a default capture, and that changes a bunch of stuff at compile time. You don't want to do that, and it's the same for pre and for contract assert and for post. Like, you cannot implicitly capture something in a precondition or contract assertion predicate. But if you add void e here, then it's void I here, then it's ODR used, and then it's fine. It's just that if the only place in which you ODR use something in a lambda is the contract assertions, and it has a default capture in it, that's still fine. This is somewhere else, it's captured anyway, so you're fine. So the act of adding the contract assertion is not going to trigger that capture. It's not going to change the compile time semantic program, which is the thing that you want to prove. Was there a question about this? Or Okay. So this is kind of syntactic, like where do you put them and like what can you not? So how does this behave at runtime? So here's the point of evaluation. I already touched on this a little bit. So precondition assertions are evaluated after the parameters have been initialized and before you start executing the body, right? So that's when the function is called. It's kind of where this boundary of like, the interface has been called, the implementation starts running, and it's kind of right in between.
And also before entering the function try block.
Yes, because that's part of the function body.
Yeah.
As per the C++.
Right.
So interestingly, if you throw from a predicate and that throws an exception, you cannot catch that exception in a function try block, which is apparently surprising to some people. Post condition assertions, as I said, after the result object value has been initialized, which is kind of cool. And after local variables have been destroyed, before the function parameters have been destroyed. So that's kind of the point of evaluation for post. Assertion statements are statements, so they're just evaluated whenever you reach that statement, because it's a normal statement. And there are theoretically four different semantics with which you can evaluate a contract assertion. I mean, theoretically there are even five, but the fifth wasn't found to be any use in practice. So these are the four that are actually useful. So you can evaluate the predicate, and if you have a contract violation, terminate. That's called enforce. That's what assert macro does by default. You can evaluate the predicate, and if it's not true, log it or something and just keep going. It's called observe. You can ignore it. You can just do nothing, not check it at all. Right? Or you can assume it and say, well, I'm not going to check it, but I'm going to assume that it's true. And if it's not true, it's undefined behavior. And then you get optimizations, assuming that it's true. It's occasionally very useful if you want to tweak your performance in a very particular part of your code, which I think finance people kind of, they do this kind of stuff, right? So that's what assume is good at. If you obviously measure, because it can also pessimize your code horribly in certain situations. So you can't always have to measure it. And so, as I said, assume we kind of excluded from this first MVP paper because it's a feature that tends to be generally misunderstood and generate like discussion and controversy. So we're going to do that as an extra paper, not in the MVP paper. So in the MVP paper, we have three possible contract semantics: enforce, observe, and ignore. And so these two we call checked semantics because the predicate is checked. And these, which you only have one in the paper, called unchecked semantics, but we don't check it. Right, ignore it, do nothing. The difference, though, to macro assert is that you don't throw away the tokens. You still parse and ODR use the expression inside. You just don't evaluate it, right? So you get the same behavior at compile time, but you don't get anything that does anything at runtime. And that's important because otherwise you can sphere on whether something's ODR used or not, and then you get this Heisenberg thing again, which you get with the assert macro, but you don't get with this. So contract, it still has to be a valid expression that needs to be parsed, but it's never going to be evaluated. So it's like an unevaluated operand, it's like size off or something. Okay, and so like which one do you get of these three, right? And like we leave that completely open. So the previous proposals had all kinds of build modes that let you say whether something is enforced or ignored, or labels that you put on assertions to say whether they're checked or not checked in this build mode or whatever. And it's kind of, you figured out that it's kind of a bit too rigid. Like there's lots of use cases where this just doesn't kind of allow you to do what you want to do. So we just say that which contract semantic you get is implementation defined. And so it's up to the compiler to figure out which flags they're going to introduce to like. And so the semantics can also be different. They don't have to be the same throughout the whole program. They can be different for different assertions, or even for different evaluations of the same assertion. So I don't expect that to be very common, but it's not prohibited. So the compiler can do whatever they want. You can say, we're only going to check contract assertions on Tuesday and only if the line number is divisible by 7. Like that would be conforming to the standard. Of course, that doesn't make any sense.
But checking it every 50th time does.
Yes.
If you're statistically sampling.
Observing something, you don't want to have log messages for every single one. So you want to leave that open what you can do with this, and you also want to leave it open whether context semantics that shows that compile time with a compiler flag, which we expect to be the most common case. Maybe you want to do that at link time, right? We also allow different station units with like different semantics and be able to link them together. If you have an interpreter, maybe you want to change the semantic at runtime. There's nothing wrong with that either. And so you get all of these options. We have a few recommendations, which I think somehow didn't make it into the slide. Okay, so I'm sorry for that. I'm missing a slide here. So this is complete implementation defined, but we have 3 recommendations. So these are things that compiler doesn't have to implement, but should implement if it wants to be a nice compiler. And we say that one recommendation is that there should be a build mode where all contract assertions are enforced, like checking, and then if it fails, terminate. You should have a build mode where all of them are ignored. That's kind of roughly equal to third macro, like CAssert with and debug and without. And the third recommendation is that enforce should be the default, which again is the same as for macro assert. So those are the 3 recommendations. Sorry for not including them in the slide, but I don't know how that happened. And so what happens when you then actually evaluate your control flow reaches this contract assert? So if the predicate evaluation is true, then you're good. Right? You just keep going. Nothing happened. Everything is correct. If the predicate evaluation is false, you know you have a contract violation. But then there are 2 more cases. And there are the cases where the predicate didn't evaluate until the end. You don't know if they're true or false because something went wrong. And something can go wrong in a way that you can recover from that. For example, you throw an exception while you evaluate the predicates. It's not true or false. It's throw an exception, but you can catch it. Right? So in all of those cases where we can recover somehow, because we're still within the machinery of the contract facility, we say that we're going to treat that as a contract violation as well. You can get your contract violation handler called and you can kind of recover, right? So if the predicate throws, that's this one here, then we treat that as a contract violation. And the other one is, we're going to talk about this a bit later, but like if evaluation occurs at compile time, basically during constant evaluation, right? And at compile time, you hit a predicate which is not a core constant expression, so it cannot be evaluated at compile time because it calls a runtime function. We treat that as a contract violation as well. You might ask, don't you want to make the program ill-formed if that happens? And no, you don't, but there's good reasons for that. I don't think I'm going to have time to.
There's a paper on that.
There's a paper on that. There are good reasons why you don't want to just unconditionally make it ill-formed. And there are even better reasons why you don't want to make the whole thing not a constant expression. Because you can fine on whether something is a constant expression, and then you get the Heisenberg problem. You don't want to do that. So this is also a contract violation. And the 4th case is you don't get to find out whether the predicate evaluated true or false, and you also don't get to catch anything because like the control flow just left your contract check and went somewhere completely different. And that happens when you long jump while you evaluate the predicate, or terminate the program, or enter a different loop, or suspend the current thread indefinitely. In all of those cases, you just cut off here. But like, oh no, there we go. You get what you get. If you long jump while evaluating the predicate, you just long jump. And then you're just no longer checking the contract. And that's what you get. And again, C++20 said it's UB, and I don't think that's a good thing to say. You don't want to add UB. We just want to say, well, it's going to execute the code that you wrote. But at least you don't get UB. All right. So here's another slightly tricky one. So if you have a sequence of contract assertions, like for example, 2 preconditions in a row, or a precondition and then a contract assertion immediately as the first statement, like a sequence of them, we say that sequence is executed once or multiple times. So that is important because there are implementations where you want to bake the contract checks into the binary, so they're kind of on the implementation side. But there are also cases where you want to check on caller side. And depending on which TUs you link together, you might end up with both. And so you're going to end up checking the whole sequence twice. And we say this shouldn't be not allowed, because then that restricts how you can implement this. You must then decide if it's caller side or callee side, and you kind of don't want to restrict that because there are situations where you want to do either or both. So the rules that we have is that you are always guaranteed to check precondition 1 before you check precondition 2. Hopefully for very obvious reasons, because if you check 2 before checking 1, you get UB. If that's no, that's bad. So you can't do that, but you can repeat the sequence and you can omit any contract checks from the repetition. For example, if the compiler can tell, oh, I already checked that. So it can throw out any contract assertion, just elide it, and that's also allowed. So typically you would either get 1, 2 or 1, 2, 1, 2. But like you could also get 1-to-1 or 1-to-2. Like these are all also allowed. I don't think they will happen in practice, but they are allowed. What's not allowed is just evaluating 1 without evaluating 2, or evaluating 2 before evaluating 1. So those combinations are not allowed. Side effects. That's another very interesting one. In C++20, a predicate that has side effects, like it modifies a global variable or prints or does anything that is observable, was just made undefined. It means that there are a lot of predicates that are undefined behavior, which is not good.
I mean, you can't allocate at that point. Like,
Right. So we said, you shouldn't have predicates with side effects. It's discouraged because you are supposed to check a condition and not do something, but like change the state of your program. But occasionally it can be useful. So we don't make it UB. You can do it, but you can't rely on those side effects happening. Right? So we basically say that if the compiler can prove that the result is going to be true or false, it can just not evaluate the predicate at all. Just replace it with true or false. And so you don't get the side effects. At the same time, because of those rules, you can get the side effects multiple times as well. So you just can't rely on whether you observe the side effects 0 times, once, or multiple times. So you shouldn't do that. Gasper?
and a typical example of this being a really important optimization principle is when checking invariants, which we don't define here, but if you model class invariants with pre and post conditionals of member functions, then those some member functions that are going to result in are going to assert a post condition that is exactly the precondition of the next one. And so we want to let the compiler say, oh, these two match up. I don't have to check this twice, right? But they're on different functions. So we effectively have to weasel word this and say, well, if the compiler can prove by whatever magical means that that this is true, it can pretend to never evaluate it, which means you don't get the side effects.
You can't rely on side effects actually happening or how many times they happen, so don't do that. But there's another twist here where if the compiler cannot prove that you get true or false, like you might throw an exception, for example, then it cannot ally the side effects, because if the predicate does throw an exception, you want to have that exception available in your correlation handler by calling the current exception. That shouldn't be elidable. But like the important thing is that if you have a Boolean expression that is side effect free, like a pure like check, then none of this matters because it's unobservable how many times you called it, right? So yeah, if you have something like this and you do this evil thing that you're not supposed to do in a precondition and you modify something, then you don't know what the value of I is. It could be 0, 1, 17, 66, no idea. And if it's false, or if it's a contract violation, your contract violation that might be invoked multiple times as well. If it throws, it can't be 0, it can't elide it, but it can still do it multiple times. So you get this, potentially the exception thrown 2 times and the contract violation handler called 2 times. Speaking of the contract violation handler, so that's what is going to be called. There's a question.
Yeah, could you give a motivating example of when a side effect would be useful? Because it's not obvious to me why you would want to have side effects.
Malloc is a side effect. It's useful. I mean, there's a lot of side effects, right, that you undo during the evaluation of the predicate. Like, you wouldn't want to have a side effect that is not undone, usually.
Another example is if you have a variable that you want to just check the value of, but it needs to be behind a mutex. Then you need to be able to lock and then unlock the mutex before and after you check that condition. And that's a side effect. But that's clearly useful. Right, so if you have a contract violation handler is called. It's a function named handler contract violation, which is in the global module. Or in a global namespace if you don't do module. It takes a single argument of type contract violation, which is this new type that we're adding to the standard library. Trans void, maybe no except true or no except false. That's implementation defined. That's something we're going to talk about. You can't call it directly. The default implementation, we don't say what it does, but we recommend that it prints some information about what happened, much like certain macro does today. And it may be replaceable at link time, like operator new and delete. The way this works is you just define your own, provide your own definition, and then it's going to be linked in. right? And then it replaces the default one. But there are situations where you don't want to allow that, according to some compiler vendors. So we said it's implementation defined if this is allowed or not. I assume that every major compiler is going to allow it. And this way you can customize the behavior. You can have your own contract violation. If you have contract violation, your this function is going to be called. And then you can go do all kinds of stuff. Get this contract violation object here. You can query it. Like it has a dot location, which gives you a source location. So you can like log it yourself to your own log stream or file or whatever, phone home, and send the information about the contract violation to your server. And then if you want, you can, there's this invoke default contract violation handler thing, which you can call to call back to the default one. So you cannot call it directly, but you can call it by this thing if you want, or you can just completely do your own, not call the default thing. So you get this object, as I said, it has 5 member functions. So you can't construct this or copy or move or assign it. It just kind of is generated by the compiler when a contract violation occurs. It gives you a source location if you want. It gives you, so comment actually is supposed to give you a textual representation of the actual expression. But it's not guaranteed to do that. So that's why it's called comment and not expression, because it can give you an empty string that's also conformal. Because you might not want to store your expressions as plain text in your binary. You might want to have a compiled flag. But like the recommendation is that this should return you a textual representation of the expression that has failed. Detection mode is going to give you what happened, and this is an enum with 2 options. Either the predicate was false or it's through an exception. And if you get this one, you know that you can call std current exception and you get that exception back. We throw it and handle it somewhere further up the stack or something. There's semantic, which tells you which of the possible semantics you had. So enforce or observe. So for ignore, you will never get called because it's not checking anything. But you can here check, am I in enforce mode or am I in observe mode? If you're in enforce mode, you know that you're going to terminate once you return from the violation handler. So if you don't want to terminate, you want to do something else. I'll talk about that in a minute. And then you have kind, which gives you basically the syntactic kind of whether the thing that was violated, was it the pre or post or contract assert? And note that we cannot use contract assert here because it's a full keyword. So then we have to use assert again, which is fine because as long as there's no paren behind it, it's not going to be expanded as the assertion macro. So there's no collision there. And all of this is in namespace contracts, which is in header contracts. So that's a new header. But you only need that header if you actually implement one of those user-defined contracts. You don't use the header. You don't need the header. You just want to add pre-post or contract assert to your code. You don't have to worry about the header at all. So it's a bit like with initializer list, I guess. You can write an initializer list without including the header. If you want to write out the type because you want to function takes those as a parameter, then you need the header. So it's a bit similar. And I expect that not many people are going to write contract violation handlers. So only those people will ever need to look into this header or include it. So, we said that we can log, we can call the default one, and also breakpoint, for example. That's another feature that we have in CSS 26 now. It's very useful in a debugger. To use a certain macro has a flag, but you can trigger a breakpoint. So now you can write all of the stuff in standard C++. If this proposal goes through, which we don't know yet, obviously, there's a hand.
Sorry, is breakpoint not a function?
Yes, it is. I think it's missing paren. Apologies for that. I'll fix it. And interestingly enough, you can also throw from the contract violation handler.
Please don't do that.
And that, don't do that. And a lot of people expect that this would just not work. Like, why did we not just make it no except? But it turns out that there are some use cases where you really, really, really need that ability. Because, think about it. If you have a contract violation, you hit a contract violation, you know that the next line of code has a bug and potentially might dereference a null pointer and crash, right? You don't want to execute that line of code. Right? But if you wouldn't be able to do this, then the only other option you would have would be to terminate the.
You could also hang the thread, which is better.
Okay, well, there are situations where you can't do that. Like, for example, in an embedded environment where you don't have threads, but I guess you don't have exceptions there either. So,
Phone home and hang the thread, please.
okay. So apparently some people, not me, but some people said that they need to be able to throw here because then it gives them a way of neither terminating nor continuing into the buggy code. So you throw an exception, you propagate it up the stack, and then you handle it. And then you say that there was a bug there, I'm going to recover and do something. So obviously for that, your code must be exception safe. You can't have no except anywhere between the place where the contract violation occurred and the place where you're going to handle it, because otherwise you're just going to get terminated again, which is what you don't want. So it's very, very brittle. But apparently somebody wants to do this and says that this is so important that if they can't get that, then they'd rather have no contracts at all. So it's going to be, I think, a very interesting discussion in the design review phase, which is where we're in, whether we want to retain this feature or not. Right now, it is SG21 consensus that we have it in the paper. So.
It's okay, I'm gonna fix it. I'm gonna propose that no accept doesn't terminate, but calls the violation handler again.
Right. So we just don't have another mechanism for this, basically, at the moment. If we have a better mechanism, then anyway. Contact assertions doing, so we have 10 minutes left. So you can use contact assertions doing constant evaluation. During constant evaluation, you can't throw, you can't long jump. None of these things exist. There's exactly 3 things that can happen. Evaluate is true, evaluate is default, or not a constant expression. Those are the only 3 things that can happen. Compile time. We just say the first one is fine, and the other 2 are contact violation. So interestingly, the contact assertion itself is always a constant expression, even if the predicate is not. And you need that. So you can't sphere on whether the expression is there. So if you put a predicate in there, runtime thing, if you try to do that at compile time, you get a contact violation. What is a contact violation at compile time? Well, at compile time, you get the same 3 semantics, draw, observe, enforce, and again, which one you get is implementation. But they do slightly different things at compile time than at runtime. Ignore does nothing, so ignore is the same. Observe and enforce, check the predicate at compile time, and if you get a contract violation, observe gives you a warning, and enforce basically makes the program perform, gives you a hard error. So there's no contract violation handler at compile time, but instead you get a warning or an error in observe and enforce respectively. Yes, there's a question.
It's expected to be able to set posts differently.
You are expected to set posts differently. I don't know.
Expected force at compile time, like for my code.
Yes, you can set them independently, but the thing is, the paper doesn't say anything about that because it's all implementation defined. So talk to your compiler vendor.
So we lost a little bit of time, so I think I'm running out of time, so I need to whiz through the rest. Overrun by much?
I don't think so.
Okay, so I cannot tell you what happens in trial
Please don't.
constant evaluation. It's a weird thing of this is sometimes expert and sometimes not, depending on how you initialize it, and nasty things happen there, which I'm gonna skip. Read the paper.
We made it work the way you'd expect.
We made it work the way you'd expect. These are the rules. Read the paper. It took me several days to go. Recursive contract violations. There were past proposals that said if you have a contract violation within a contract violation, then you don't actually call the violation handler anymore because then you get the stack overflow. But then that means that every code that you call in a contract violation handler is potentially unsafe because you don't check assertions anymore. That's bad. So instead we said, you just get what you get. Like if you have a contract violation handler within your contract violation handler, then it's just gonna get called recursively. And if you get an infinite recursion, you get a stack overflow. And then you know that there's a bug that you have to fix. Yes.
Can you debug contract violations?
Sure, it's just code. You can debug contract violations.
Yes, they go on the stack. Normally, your debugger's gonna know what to do.
What's the context for pre and post difference in the function which is currently called or outside of it?
So we have 5 minutes left, so let's just not take any more questions. I just really want to get through the material and then we can discuss everything else at the bar. Undefined behavior. So we don't introduce new undefined behavior, but we don't prevent things that are already undefined behavior somehow magically from being undefined behavior, because how would we do that? Don't reinvent how the language works. So if we have a predicate here that adds 2 integers together, integer addition overflow is undefined behavior. Compiler can assume that this never overflows, and then this is basically always going to be false. So the compiler can just say, yeah, I'm just going to assume this is not UB and just replace this with pre-false, which is maybe a bit surprising when you see this first, but this is just how the language works. Another example is if you have UB just after you check the precondition, that's probably quite common, right? So you check that it's not null pointer, so you can call this and it's not going to be UB. But indeed, if it's ignored, then it's still UB, right? If it's enforced, you know that you're going to terminate here. You're never going to get to that line. So you're good. If it's observed, then you will get to that line. And that is undefined behavior. And the compiler could just optimize out this whole thing and all code calls that lead to that, including the conflict check itself. You don't really have a means to prevent that in the language. In practice, this is never going to happen because the context correlation handler is going to be in a different translation unit. So it's going to act as an optimization barrier. So this is never actually going to happen in practice. But technically, this is still UB and the compiler could like the whole thing. Okay, I'm almost done. What do we not have in this paper? These things. The first one is probably the most painful one. You can't put pre and post and virtual functions. That's hard to get right. We have a paper. We are currently still actively discussing it. We don't want to delay the rest. So we're going to do this as a separate paper. But I'm pretty sure we're going to get it in C++26 as well, on top of this. The second thing that we can't do yet is ability to refer to values at the time of call in post, which C++20 contracts also didn't do, by the way. Like, for example, post condition of pushback is that the old size was this and the new size is old size plus 1. How do you get the old size, the size from before the function was called, right? We don't really have a way of doing this, except we do. Gasper and I together wrote a paper that explains, and Gasper came up with the idea originally, I think, a few years ago, that you just use something like a lambda capture, and that's going to be executed when the function is called, and then the extra predicate is going to be executed when the function returns, and then you can in the capture say old size equals size, and then in the predicate you can say size equals old size plus 1, and that's how you check the precondition of pushback. And we don't have this in this paper. It's a precondition post-condition capture is an additional feature on top of this, which we're again going to be doing in a separate paper. But again, very much hopeful that it's going to land in C++26. You can't optimize based on an assumption that predicate is true. So the assume semantic, we don't have it either. We can't have predicates that cannot be evaluated at runtime. For example, if you call a function that has no definition. Some people want that. We don't. Our paper doesn't support that. It doesn't support all kinds of extra annotations and flags, like ways to like control what the semantic is going to be. We're going to again do that post C++26. We can't have post-condition functions that do not return a value but do something else like throw. And we don't have invariants like class invariants and loop invariants. We don't have that. But for all of those things, we have ideas how to do them. For the first three, we have like very concrete ideas how to do this, and I very much hope that these are going to land in C++26. These ones are more far off. We don't have fully fledged proposals. We have an idea how to do that, but we don't know this is how we're going to do this. So we're probably going to have to wait for C++29, and that's it. Thanks.